Hello, today we're going to see some problems about motion, the fundamentals, as we said in chapter 1, the description of motion. The idea, as we already saw in the lectures, is that we want to go, let's say, from one position, let's say our home to school. So that's going to be UCF, right? And let's say we're going with a bike, and we're here. And the question, of course, is how can we describe this motion from going from home to school? For the purpose of this example, let's pretend that we start counting the time when we are at home, and we reach UCF at some time. Let's say it takes us 100 seconds. Now we're describing our home as the initial position, which of course is going to be the origin of coordinates. So we can remember, from our frame of reference, we can describe a coordinate axis where the horizontal position is going to be x. We're going to call it x, and we're going to count it, of course, in meters. So then we can track the motion of our motion from home to campus. Now, if campus is, let's say, for the purpose of this example, we call it x2 position, it's 1,000 meters away, right? The first question that we can ask is, we're going to try to find the main components of the motion. And we said we can start by analyzing what's the displacement. And again, displacement is final position. Let's actually keep the notation. Displacement is final position minus initial position. In our case, that's going to be, of course, 1,000 minus 0, which of course is 1,000 meters. So we have the position, we have the displacement, right? Then we also have the time interval, which is a way to say how much or how long does it take us to do this motion. And time interval defined as the difference. What's the difference between being at home and being at school? What has changed in terms of time? Mathematically, we analyze that by defining the difference in time is a subtraction. So we have to subtract 100 minus 0, which of course is 100 seconds. So far we have the displacement and we have the time. And we might be wondering how fast did this happen. And when we want to achieve how fast something is happening, of course, we are using velocity, which is the ratio of change of position with respect to time. And of course, velocity is going to be, or it is defined as the change in position over time. Again, remember, it's a ratio, so it's telling us how fast we are changing our position with respect to time. Now, if we introduce those numbers, we're going to see it's 1,000 divided by 100, so we get 10. And 10, of course, this is meters and this is seconds, so it's 10 meters per second. Now, there's one thing to, let's make sure, didn't work well. So let's make, let's realize one thing from here. Maybe I can use this. There you go. If I say the velocity is the ratio of change of position with time, I can come up with the solution is 10 meters per second. Now the question is, am I riding my bike at 10 meters per second all across the path? Now in general, this could be true if the velocity was constant, but what if there was a light traffic here, right, in our lane, and at some point we had to stop our motion. At that time, of course, velocity would have been 0. And so the velocity that we have described this motion with which is 10 meters per second, doesn't hold anymore. Here velocity is not going to be 10, it's going to be 0 because I'm standing waiting for the light to turn green. Now then, what is this 10 meters per second telling me? It's actually not telling me the velocity at every instant in time, but it's actually telling me the average velocity, where we write here AVG for average. Now the idea of the concept of average is a very simple one. We're just taking a description of the overall motion. This is the same as if you want to calculate the average height of the students in class, and then you add them all together and divide by the number of students. Now that average number doesn't mean that every one of the students has that height, but rather that the average student, like a typical student, could be described as having that average height. In some instances you might find, obviously you will never find that in real life, but in some instances you might find that all the height of all the students is the same, and so the average is going to be exactly the same as the height of each one of the students. But in general that's not the case. There's going to be some that have higher height than the average and some that have lower height than the average. The average velocity works the same way. Average velocity is just a description of the entire motion. Instead of that, we're going to also find that at every instant in time we can define what is the velocity, the instantaneous velocity that we just described as v. Now v in this instant, whatever that is, that's going to be 0 when the light traffic is red. But whenever the light traffic turns green, I'm going to go back to UCF, so my velocity is going to be non-zero. In fact, the velocity needs to be even larger than the average velocity to compensate for the fact that I have spent some time standing here. So velocity is actually going to be larger than the average velocity, right? To compensate, it's expectable maybe that the velocity also could be higher here. It depends. But the basic idea here of average velocity is just describing the entire motion of the object. Now let's realize something about the average velocity. The average velocity is given by the displacement that we're considering, which is the displacement in a particular motion over the time interval it takes. Now the instantaneous velocity, however, could be analogous to the speedometer of your car. So you're seeing how fast you're going at that given instant in time. Now as we have seen, there might be instances where instantaneous velocity, which is the velocity at a certain given instant of time, is not exactly the same as the average. It's going to be lower or it's going to be higher. Now the question is, how can we really describe velocity? Velocity is an average. In fact, it's always the displacement over the time. Unless there's a certain amount of time, it's impossible to describe velocity. I need to always let some time to pass. Now to have a better approach to instantaneous velocity is obviously instead of taking the entire displacement or the entire time, I could take a smaller portion of the time. So in fact, if I wait 1 second while I'm driving down the highway, the velocity is not going to change really in 1 second. I could do that also in 0.1 seconds or 0.01 seconds or 0.001 seconds, and the smaller that the interval becomes, the more close that the average velocity comes to the instantaneous velocity. We will not study that in physics 2053, but in calculus physics you see that in fact the instantaneous velocity is mathematically the limit when the interval goes to 0 of the ratio of displacement over time, and this is of course the definition of the derivative of the position with respect to time. We don't study this, but this is just to complete the idea. We go from average, which is overall description, to particular instance. Now we can see some more examples of displacement in one dimension, calculating average velocity, seeing if we can find instantaneous velocity, and seeing what we can say about the displacement of the motion. So let's take problem 4 from the discussion section. It says that the student is driving its car, or her car, 10 kilometers, so the displacement is 10 kilometers, and it takes her an amount of time of 30 minutes. Now the question is, what is the average velocity of this student? Now to describe this, of course, we need to find first, or we need to write first, the definition of average velocity, which of course is the displacement over an amount of time. In this case would be 10 kilometers over 30 minutes. Now minutes and kilometers are not nice units. In international system we prefer to use meters for distances, and for time we use seconds. So our goal is going to be first to change kilometers to meters and minutes to seconds. So we can do that as follows. 10 kilometers, 1 kilometer, it's equal to 1,000 meters. So wherever I have kilometers, now I can write 1,000 meters. So I'm going to have 10 of 1,000 meters, and of course this is kilometers. So you see it's exactly the same thing. So at the end I just find that I have 10 followed by 3 zeros, or 10 to the 4 meters. Now we can do the same for time, and in this case we have 30 minutes. Now the key, of course, is to realize how we can convert from minutes to seconds, and as you know, 1 minute is equal to 60 seconds. And so I can replace minutes for 60 seconds, so that's going to be 30, and now instead of minutes, I'm going to write 60 seconds. And so if I multiply this, I'm going to find it's 1800 seconds. And finally, I can make just the division of 10,000 meters over 1800 seconds. Let's just keep this here. And so I can write 10,000 divided by 1800 seconds, which is going to give, which is of course 5.56 meters per second. Now we found the result in international units. We could have made the calculation as well in the units of the problem. So if we do the problem in the units of the problem, we're going to have, for instance, let's say kilometers per hour instead of kilometers per minute. We're going to find 10 kilometers divided by 30 minutes. Now we know that 10 kilometers is 10,000, well, we can keep 10 kilometers, but now 30 minutes is how much? It's half an hour. So I can write 30 minutes into units of hour, and so I can divide this, and 10 over 0.5, of course, is 20, and it's kilometers per hour. Now obviously this and this result are the same, they're just expressed in different units, and as we saw in class, units are just the standard. So when I'm saying that my average velocity is 5.56 meters per second, it is the same as saying that my average velocity is 20 kilometers per hour. What I'm saying is that I take 20 of the unit standard called kilometers in 1 hour, which again is the unit standard of 3,600 seconds. So this is just a way of saying that the same result can be expressed in different numbers, and what's the concept of average velocity. Now this is the average velocity for the entire motion, but it is expectable that if she is driving through the city, she would not be driving at a constant velocity of 5.56 meters per second or 20 kilometers per hour, which is actually pretty low. But she will be at some point going a little bit faster, and at some point a little bit lower, because maybe there's a light traffic, maybe it's a zebra crossing, there's some children running in there, she needs to brake, she needs to let life continue. Let's see another problem. This is problem 6 from discussion, and this is in case of a robot rolling through a shop, and the robot, it says it's traveling at a constant velocity of 4.25 meters per second, and the distance it covers is 17 meters. Now the question is, how long does it take to make this motion? Sometimes we're going to find problems where we're given velocity and displacement and we're asked about time. Sometimes we're given time and displacement and we're asked about velocity. Sometimes we're given velocity and time and we're asked about displacement. At the end of the day, we have 3 variables in here, and with 2 of those we can always find the third one, because they're all connected through the average velocity equation, which of course is delta x over the time it takes, or delta t. It doesn't matter. If we take delta t and we take the initial time as 0, then delta t becomes t minus d sub 0, which of course this goes to 0, so it's just simply t. So we can just simply write delta x over t. Now the question here is we want to find t. This is what we don't know, and we have delta x and v average. In every problem, write down maybe a small cartoon about the situation to understand exactly what the problem is stating, making sense or making sure it makes sense, and write down your information and write down what you want to find. Then you write the equation, you identify what equation is the one that's going to give you the information, and then you can work from there. In this case, we have the time that we want to find, and we have the average velocity is equal to the different time. So how can we find out this? Well, we need to solve for t. In this case, what we can do is just multiply times in both sides. So we have they cancel, and then we just need to divide by T average, V average, excuse me. So this cancels, and so we find finally time. Now, of course, you can do just much more simpler. This is dividing, so it passes multiplying. This is multiplying times 1, so it goes dividing. And then we can replace our numbers in here. So we have 17 meters, and we have 4.25 meters per second. And so we can finally solve and find out that the answer is 4 seconds. Now let's take a second and see that when we have meters per second, let's use this area over here. How do we divide meters by meters per second? So remember, you have meters and you are divided by meters over second. So of course you go in diagonal. So this is meters times second, and you go in diagonal. This number is divided by 1, so you just divide by meters. Meters and meters cancel, so you just have seconds, which is of course the unit of this problem. So the solution, 4 seconds. This problem is a good example of the difference between displacement and distance, and between velocity and speed. In displacement, we do not care about the actual track or path followed, and in distance we do care about it because we have to account for everything. In the case of velocity, we do not care about the actual path taken. In the case of speed, we do because we use distance. So the problem states that there is a runner on a 200-meter track, so the entire track is 200 meters for whatever reason, and then the runner covers 1 lap in 2.5 seconds. Excuse me, 25 seconds. Otherwise, 25 seconds. So, first thing that we can consider is what is the displacement, what is the distance covered. Displacement is given simply by the equation. So we just need to put the final position and the initial position. But we immediately note something. If this track is a loop, the initial position is this starting point, and the final position is going to be after 1 lap, the same point. So whatever that number we want to associate to that position, of course this is going to be the same. We call this x sub 2. Right? So immediately we see the displacement is 0. Of course the athlete has run a lap, but its displacement is 0 because he ended up in the same position. This distinction is going to be important later on when we calculate energy and work done for non-conservative forces. The question, however, is how much distance has it covered? Now displacement doesn't account for the fact that the athlete ran through. Displacement accounts just the fact that you start and then in the same. It's just asking what is the difference between initial and final position. In the case of a distance, however, we do care about the actual path taken, and of course we know if the lap is 200 meters, the total distance is obviously 200 meters. Now, of course, once we have established this, we can then wonder what is the average velocity and what's the average speed. So the average velocity is going to be given by displacement over the time taken. Now displacement we just found is 0, the time taken is 25 seconds. What's the average velocity? 0 meters per second. We're counting meters and seconds. However, for the speed, sometimes we can use S, but I rather don't use S because we can then confuse it with actual distance taken in some textbooks. In speed, we're going to be considering the actual distance and the time taken. And in this case, it's going to be, of course, 200 meters in 25 seconds, which is 8 meters per second. And so we see, when we discuss displacement, we're just considering initial and final position. If they're the same as in the case of a circular track, of course displacement is 0. If this is not accounting for the path, right? This does not account for the path. But this one, which is distance, does account for the path. Likewise, average velocity is not accounting for the path. Average speed, it is accounting for the path. So we see a difference in here. So we have some concepts of displacement, time interval, velocity, average velocity, and speed.